In this module, we examine two current hypotheses about basal ganglia function in movement control by reviewing scientific and clinical evidence for these hypotheses. A lot of what we know about basal ganglia function comes from the study of people with Parkinson's disease. Parkinson's disease results in 4 cardinal symptoms, which you can use a mnemonic TRAP for easy remembering. First is tremor, which is a 4-5 Hz resting tremor that reduces or goes away during movement. Rigidity is resistance to passive limb displacement. Akinesia or bradykinesia simply means lack of movement or slowness of movement, and postural instability, which results in high susceptibility to falling. The defining symptom of Parkinson's disease is akinesia or bradykinesia. These are the symptoms like tremor, need not be present in all Parkinson's patients. However, all patients show some form of lack of movement or slowness of movement, or akinesia or bradykinesia. Neurophysiologically speaking, Parkinson's disease is defined by the death of the dopamine-producing neurons in the substantia nigra, such as patients with Parkinson's disease will improve their movement slowness when taking medications that increase their dopamine levels. Let's look at how slow movements shown up in bradykinesia and Parkinson's disease informed our ideas of basal ganglia function. So in the early 2000s, the prominent theory was that slowed movements in Parkinson's was a compensatory response from the brain to reduce movement inaccuracy and movement variability. That idea changed after a study led by Pietro Mazzoni, where they asked Parkinson's disease patients to make reaches to targets at a pre-specified speed without having any visual feedback of movement. So they told patients that the trial was successful only if the speed of the reach was within the requested range. And patients had to repeat the trial if the speed was outside the requested range. Surprisingly, for each given speed, the endpoint accuracy and the velocity of the movement was similar to controls. So if you look at the left and the middle figure there, the left figure is showing peak velocity. Clear symbols are Parkinson's disease patients. You can see that for each given requested speed and for the different distances to the target, Parkinson's disease patients are showing movements that are as fast as healthy controls. The middle figure there looks at systematic extent error, so how accurate the movements are, and you can see again that Parkinson's disease patients weren't different from healthy controls. So patients were perfectly capable of producing movements of normal speed and accuracy. But if you look at the figure on the right there, that's showing you the number of trials it took them to hit that criterion. So they required many more attempts. If you look at those clear symbols there again, those are the Parkinson's disease patients requiring many more attempts to produce the reach that was as fast as the requested speed. So this suggests that under normal circumstances, Parkinson's disease patients reach slowly not because of a strategy to improve accuracy, but due to a changed estimation of the costs and benefits of moving fast. So for Parkinsonian brains, movements are estimated to be more costly or less rewarding than in healthy brains, and thus their movements are less vigorous. They show lower speed and smaller amplitudes. So the dopamine-dependent circuits in the basal ganglia that are known to be impaired in Parkinson's disease are thought to modulate movement vigor. And this is thought to support our first hypothesis that the basal ganglia modulates movement vigor. Another piece of evidence for a basal ganglia role in movement vigor is paradoxical kinesia, which is the fact that Parkinson's disease patients can spontaneously improve their bradykinesia under urgent conditions, like when escaping from physical danger. There have been many anecdotes of similar scenarios. For example, Parkinson's disease patients who are even unable to get out of their chair, very severe patients, can run out of a burning house. So under ordinary conditions, where there's no urgency, movements are bradykinetic. So if you look at this gentleman shown on the left there, but the same gentleman can catch the ball with normal speed and accuracy, particularly when the ball has a risk of falling if he doesn't catch it quickly. And similar experiments have been run by Matchluck et al., shown at the bottom there, where they've compared scenarios where patients are asked to reach as fast as possible to pick up a ball that's stationary versus a ball that's moving. And patients reach 50% slower than normal if the ball is stationary, but at near normal speeds when the ball is moving, and even faster when the ball is about to fall to the floor. A second hypothesis is that the basal ganglia is responsible for selecting motor actions. So according to this view, activating the direct pathway helps select a desired motor program, and activating the inhibitory indirect pathway inhibits competing inappropriate motor programs. And co-activation of these pathways is thought to have a focusing effect, allowing appropriate actions to be selected and inappropriate actions to be inhibited. Evidence for this idea comes from basal ganglia disorders where there's hypokinesia, insufficient movement, like in Parkinson's disease, or hyperkinetic movement disorders like hemibolism or Huntington's disease, where there's excessive movement. And we'll go through that next. So bradykinesia in Parkinson's disease has been suggested to result from an overactive leash or excessive globus pallidus interna inhibition of the thalamus. And this is supported by clinical evidence that lesioning the globus pallidus into movement disorders where there's an excessive amount of movement or hyperkinetic movement disorders have been thought to occur because the globus pallidus interna fails to inhibit the thalamus, so a weak leash if you like. For example, experimental and clinical lesions of the subthalamic nucleus, part of the indirect pathway, causes hemibolism. Bolism is simply large amplitude involuntary movements of the proximal limbs. So this is just bolism on one side, and this is thought to occur because the subthalamic nucleus has an important excitatory output to the globus pallidus interna. It energizes the leash holder. Without the subthalamic nucleus input to the globus pallidus interna, the leash holder effectively has not enough energy to inhibit the thalamus, and the thalamus overstimulates the motor cortex, causing involuntary hyperkinetic motor symptoms. And these might include other symptoms such as chorea. Chorea, similar to the word choreography, stands for dance-like jerky movements. Dyskinesia, which again is involuntary movements. Hypertonia, increased muscle tone. Athetosis, which is writhing movements of the extremities. And bolism, which I've mentioned earlier. To recap, there are two primary hypotheses about how the basal ganglia affects motor function. First is that the basal ganglia modulates movement vigor, similar to controlling the dials of a jukebox to change its volume or the bass levels. The second idea is that the basal ganglia modulates action selection by selecting desired actions by activating the direct pathway or inhibiting competing actions by activating the indirect pathway, similar to pressing play or stop buttons on a jukebox to play or stop a song. Current evidence can't yet arbitrate between these two hypotheses. Many people believe that both may be true. And this concludes the second module of the basal ganglia lecture.